In this video, I will introduce the surface integral, an integral to calculate the area of a parametric surface. The goal is to give you intuition behind the formula and to show the connection with previously learned material. Suppose we want to calculate the surface area of half a sphere. This is easy, as you know the formula of the surface area of a full sphere. As we are only interested in half of the sphere, we divide it by 2 to obtain 2 pi times the radius squared. But what if the object we are interested in does not have a known expression for the surface area? The process is very similar to how we calculated the Jacobian for coordinate transformations. So let's revisit how to calculate the area of a shape in 2 dimensions. To calculate the area of a parametric shape in 2 dimensions, we need to determine how an area element changes when changing coordinates. We assume we can parameterize S with coordinates u and v, where u and v are in R as seen on the right image. To calculate the area, we need to find an expression for the area element delta A in terms of u and v. One method is to find a description of the vectors A and B, the sides of the parallelogram that approximates delta A. Vector A is the difference between its end and beginning point, given by the vectors in the left image. And when delta u is small, this difference is approximately the derivative of r with respect to u times delta u. The same can be calculated for vector B. What's left is to determine the area of a parallelogram with the vectors A and B as its sides. We know that the area of a parallelogram in 3D space is given by the length of the cross product of the vectors. The parallelogram, spanned by the vectors A and B, can also be seen as a parallelogram in 3D. Just take it to be flat on the z is 0 plane. So we see vectors A and B as vectors in R3 by setting their z-coordinate to 0. And therefore, the derivative of z with respect to u or v is also equal to 0. The area delta A is then approximately the length of the cross product, which for a z-coordinate equal to 0 is relatively simple and given by the expression on the right. We now have an approximation of the blue area element of S in terms of u and v. We need to sum over all such area elements and make them very small by taking the limit of delta u and delta v to 0. The area of S is then given by this integral, but in principle, the integrand on the right is the length of the cross product of the derivatives of the position vector r with respect to u and v. The fact that the calculations were in 2D results in the explicit expression seen here. Up until now, S was an area in 2D. What happens when we need to calculate the area of a surface in 3D, like this surface S? We again assume that this surface can be parameterized by coordinates u and v. How do we find the area element delta S in terms of u and v? Again, we want to approximate the surface by a parallelogram. And although it might seem like a rough approximation, as the surface might not be flat, our intention is to take the limits of delta u and delta v to 0, making the approximation valid. The sides of this parallelogram are again the vectors that approximate the sides of delta S. To determine the vector A, we need to subtract the vectors pointing towards the end and beginning of A. These vectors live in R3, but as the endpoints are on the parametric surface, they can be described using only u and v. Vector A can be approximated by the derivative of position vector r with respect to u times delta u. As vector r is in 3D, the derivative contains the partial derivatives of x, y, and z with respect to u. The same can be derived for vector b. The area of the parallelogram spanned by the vectors a and b is the length of the cross product of these vectors, resulting in an approximation of the area of delta S in terms of u and v. We again need to sum over all such area elements and take the limit of delta u and delta v to 0 to find the area of the surface. We end up with a so-called surface integral, and this is exactly the same as the formula for the area of a shape in 2D, but there the z-coordinate was 0. I hope this video developed some intuition behind the formula of the surface integral and have fun applying it to any surface.